Recorded lecture for Tuesday, October 29th. What we're going to talk about today is OCL, or the Object Constraint Language. What I'd like to do, instead of going through a presentation, is to walk through a paper that actually is a tutorial paper for OCL. So what I'd like you to do is also to read the paper, but we'll walk through and look at some of the highlights and discuss, I think, some of the main points to do with things like, say, the type system for OCL and some of the operators used in the language. Now, if you actually start at the course web page and you scroll down, you'll see we had this announcement on Tuesday, October 22nd, readings for the next 2 weeks, and one of those was this OCL tutorial by Jordi Cabot and Martin Gurgola. And so if you click on there, you go to this modelinglanguages.com website, which I think is just in general a great website to take a look at. You'll notice that this website is maintained by one of the authors of the book that we're using in the course. You'll see the book over here on the right. And so you can follow this link here to download the PDF of the chapter that we're looking at. There's also an online presentation that you can go through some slides. I don't think it's actually the talk, it's just the slides from a talk that was given by Jordi Cabot. Okay, so once you actually get this downloaded, you'll see this. It's a fairly short tutorial. It's around 33 pages, and doesn't, of course, in 33 pages go into a lot of depth about OCL, but at least gives a good overview of the language. And the first thing that they talk about, and I think this is really a good point to start with, is essentially why bother with OCL. All right, we have something like UML, we have other visual modeling languages, and we of course have textual modeling languages, like some of the languages that maybe we're working on for projects, or a couple of the languages I've discussed. And so, why do we need something like OCL? Well, one of the reasons this is needed is that a lot of developers really prefer using graphical modeling languages, so things that look like UML, or say things that involve maybe not UML, but other graphical widgets where they're dragged around on some kind of a canvas and information is added. And the good thing about these is you do get some expressivity with them, you do get, I think, ease of use, but it's quite challenging actually, when you get to motivation here, it's quite challenging actually to say everything that you would want to say just in a graphical notation. There's several examples given here where there's this inability to express certain important properties using graphical notation. The example they give is some kind of e-rent car rental specification. They provide just a class diagram here that shows various classes in the system. So there's cars and there's rentals and branches where people go to rent cars, and quotations and customers, and then this special type of customer, which is a blacklisted customer, maybe someone who doesn't clean out the car when they bring him back, or that somehow winds up not paying or whatever. So they get blacklisted so they can't rent cars. Now, some of the things that we can't actually specify directly in this model are things like this first one listed here. If someone's blacklisted, can they rent a new car? Obviously, there's some mapping in the system already between a blacklisted customer over here and between some rental. If there wasn't, they probably wouldn't have been blacklisted in the first place. But the model given just at the graphical level doesn't have any way of indicating, for instance, that once someone is blacklisted, they shouldn't be able to continue renting cars. Other questions would be things like, how's the price of a rental calculated? What are the conditions to be able to extend an existing rental? Should you have to have a valid driver's license through the entire rental period? Do you need to be of some minimum age? And a few other things here. So, these are the types of things that we would like to be able to state, and especially if we think about, say, generating code from this model, we would need to have answers to these questions, or we couldn't generate code that wanted to do what we wanted the system to actually do for us. But there's also other examples, and I think if we talk about this limitation where, they actually mention this here. This means the graphical notations can only express a limited subset of all the relevant information in the domain. If we also think about the example that we had using alloy in homework 2, something like the family example, I think we see this quite clearly there as well. We have a lot of, the model itself is very simple, right? We had people, and we had men and women, and some subset of these men and women were married, and then we had various properties on these. People that were married had a spouse, and people in general could have siblings and children. And what we saw is this gave us an amazingly unconstrained model, where we had a lot of behaviors in the model that we really didn't want to see. For instance, someone could be their own child, or someone could be married to themselves. And so what we did in that homework assignment was we added a number of facts, and these facts were things that constrained the model that said, I'm stating a fact that a person can't marry themselves, and therefore a valid model that we have is then one where this does not occur. Right, so these are the types of things we would want to note down, and if we were to use something like UML, and we treat these different categories, person, man, woman, married, as, say, classes in the diagram, we would come up with some type of diagram that, with similar types of notation where we'd use, where we'd have classes and we would have other classes that extend those. So we have these generalization arrows, like we see here, or then we would have various associations. For instance, we would have something like 0 ... an association here to say that a person can be associated, back to other people. So it's a circular association, as saying that they have children or saying they have siblings. Right, but then we would need some way of going in and noting down all these facts. And if we were writing code, we would just write this in Java. We would do things like if you tried to insert a new person into children, you would check, and you would check the various conditions we were looking at. Am I saying I'm my own child? Am I saying that my brother is my child, or that my mother is my child? But OCL gives us a way to note down these types of constraints in the models that we build. Okay, so what the authors then do is they describe OCL at a fairly high level. There's several important points that they mention here about the way that OCL works. I think these are useful to know, so you have an idea of, in some sense, the computational model that OCL follows. Number one, OCL is typed. And what this means is that when you have some type of OCL expression, then it evaluates to some sort of type, and we'll take a fairly detailed look at the types as they do here in this tutorial chapter. In general, the types are either things that come with OCL, or they are based on types that come out of the diagrams. So types like the various class types that we see here, or some combination of the two. So for instance, OCL has sets, and OCL has integers, and so you can have sets of integers, but you can also have sets of customers. OCL is side effect free, and what this means is that OCL can query the model, and OCL can constrain the state of the system that is being modeled, but we can't have an OCL constraint that would do something like update the model. So OCL views the model as this read-only thing that it can reason about, and that it can constrain, but that it can't modify. Right? So we don't, in other words, we don't have a model where, say, these relationships that we want to define don't hold, and then OCL goes through and somehow cleans that up. Instead, OCL, just like the facts in Alloy, would prevent these versions of the model that we have from being valid in the first place. So if we added a constraint here saying that people that were blacklisted can't rent vehicles anymore based on the date that they're blacklisted, then OCL doesn't work by then going through and finding all the rentals where it doesn't hold and throwing them out. It just says that those types of rentals can't exist in the first place. Right, and finally, OCL is declarative, and so what we don't have is we don't have imperative constructs. We don't have things like assignment. OCL looks a lot more like, depending on the part of the language we're looking at, various parts of specification languages, functional languages, or logic languages. It has these features. There's parts that look a lot like predicate logic or like alloy. It has these features in here that have a very declarative feel, so you write down what OCL should do, but you don't actually write down some algorithm in OCL that then goes through and takes steps and adds to counters and this kind of thing. And finally, they make the point of saying that OCL is a specification language, and I'm not really sure that this is that different of a point than the last one, but the important point maybe when you're using tools based on OCL is the fact that this is the definition of the language, but there could in fact be implementation details that mean different OCL interpreters, different OCL tools would use OCL in slightly different and maybe potentially incompatible, but at least different ways, right? So OCL doesn't tell people how an OCL tool should be implemented. It says what OCL is, and then a tool vendor would figure out what OCL actually does. Right. I'm not going to dwell on this part. Again, please read through all this, but we can go through very quickly just to give some very high-level examples of how you would use OCL within these categories. Probably one of the more common areas, and I would say one of the first. OCL really started off as basically a constraint language, and then grew to become a more flexible language that you could use to do code querying and that you could use to identify parts of your model in transformations. But initially the goal was really, as the name would suggest, to add constraints to the model. And so here's an example of the constraint given in the middle of the page. And you have to include a context here because the context says which of the pieces of the model this applies to. Right, so if we go back up here, you can see we have this class quote, and this has a value field. And so now what we're doing is we're creating a condition here, some kind of a constraint, where we say that within quote, we're creating an invariant, and the invariant is named quote over 0. And what we're saying is that the value of the quote and self is essentially like a this pointer in Java or C++, right? It says the current instance of quote. So if I have an object that's an instance of quote, the value has to be greater than 0. This is a fairly simple condition that we're adding, a fairly simple constraint. We could have a more complex constraint, and this is where we start seeing more of the use of OCL and some of the language features we get for things like navigation and talking about groups. So we have this blacklisted class, and so our context is blacklisted. And what we want to say here is that I can't rent a car once someone is blacklisted. So at some point they become blacklisted, there's some date when this begins, and then they can't rent cars anymore. And so we see a couple of things here. We see this notation where we have this self.rental and then an arrow and for all. And we get that because if we are in blacklisted itself doesn't have a rental property. And you see this doesn't have a rental property either, but most likely the actual implementation of this would, because we have this association. Right, this association has rental listed here. Let's see if I can highlight that individually. Zoom in a bit more. You'll see it's down here, this association. And so this says that a customer, which who could be a blacklisted customer or just a normal customer, has a rental and they have one or more of these rentals. Right, and then rentals have drivers. Right, so we see drivers over here also with one ... And so because we have this link between customers and rentals, where customers have rentals, then we can actually navigate through that. So let's go back down to the invariant. So we can say self.rental, and this navigates through this rentals association and gives us back then all the rentals that this customer has made or would make. And so again, this is constraining, just like the facts and alloy. So what we then say is we say for all of these rentals, right? So this is for all is basically our universal quantifier. So this would be like all in alloy. And then we have a variable which stands for the rental. And we say the start date of the rental is less than the blacklisted date for the customer. So we're basically saying that any rentals this customer has, they started the rental before they became blacklisted. Okay. Let me briefly go. I think that's probably the most important one to cover, but let me just briefly continue through the tutorial and look at these other ones. We have initialization expressions, so if we wanted to be able to say what the starting value of some type of field in the model was, like here premium, which means the customer is a premium customer, we say, well, this starts as being false. And then this next point here, derived elements, I think is something which is quite an interesting thing. What this is really saying is, well, you can have information in the model that isn't actually, I guess you'd say it's not explicitly in the model in the sense of it's not, if you imagine that you had object instances of these classes, this isn't something that you would implement as some field that just stores the value. Really, we're saying this is some kind of computed information that we're storing in the model, and this computed information is based on other things that are in the model as well. And so in this case, what we have is, again, we have the context, and this is within customers, and we have some sort of discount. And if we see if it's up here, we see it's here. It says discount is integer, and of course this doesn't say anything about how the discount is computed or where it lives, other than the fact that it's in the customer. It doesn't constrain us to say that this has to be a field that's implemented, say, in a Java class. If we created a Java class for this, really what we're saying is this is derived. This is based on other information. So in this case, we say, well, if we're not a premium customer, and then what we do is we look at the rentals, and this, I don't want to go into a huge level of detail with every little piece of this, but this is essentially a query. It's, select queries in databases. We can do selects here, and this says, give me back all the cars such that the category, I have to look up here. So this is, I believe, all the car groups. So give me back all the car groups. So we see we can navigate through here. We have rentals, and the rentals are associated with cars, and then the cars are associated with car groups. So we can just, in some sense, follow the lines through the model and look at the name of the association to get there. So I misspoke a moment ago. The C is actually the car groups, and what we get is we get back the car group for each car that we've rented. And then we have what would be a where clause in a SQL query, and we say where the category of the group is high. So this is some kind of high-end, like a luxury car. And then we take the size of this. And so if the size of this is greater than or equal to 5, in other words, if the customer has rented premium cars, if the customer has rented high category cars 5 or more times, then what we'll do is we say, well, then, but they're not a premium customer, right? So they've rented enough cars, we'll give them a discount. We'll give them, so this is 15, that's what the discount is. So you can imagine that as 15% off. So they're not a premium customer, they've rented a lot of expensive cars though, we'll give them 50% off. Else we give them 0% off. They're just a regular customer. If they are a premium customer, then what we get is we get a 30% discount. Right, so this also uses premium. Sorry to keep scrolling back and forth here. Right, so this really uses these last two fields in the customer, premium and discount, as well as this category in the car group. Right, so again, the nice thing here is we just have this derived information, and this information, you could easily imagine generating code for this, where when we go to look up the discount amount, we actually look essentially in real time, or maybe we have this pre-computed, and we just recompute it regularly to see if they're not a premium customer, what their rental history is, and then we base the discount on that. Now the difference between this and the initialization up here is that the initialization really is just initialization. This doesn't tell me that this premium field, where I'm saying whether they're a premium customer or not, stays false. It just says that it starts as false. And then maybe, of course, at some point the customer becomes a premium customer and this becomes true. With the derived elements, instead, what we say is when we're looking this up, this is something that we compute. This is based on other information in the models. This isn't just initialization stuff. This is what we do whenever we need to get this value. Okay, query operations, we've already seen an example of this. We've already seen these operators. I'll let you just read this, and I'll keep scrolling. And then I think this is maybe a bit much to go through in our talk, so maybe it'll be easier for me to, if anyone has questions on this, to go through this in class. This would be a way that you could, similarly to with derived information, a way that you could actually describe the business logic behind certain steps in the model. So this is actually describing what happens when you create a new rental. And we see we have some operations where this is new and it's a rental type, and we have checking the dates, and so we have the quality checks, and then we have this use of any, and any is equivalent to in alloy, where we had something like some, or where we say exists, except what it's saying is that give me any of these C where this is true. So we could have maybe 10 different entries here, and it could just non-deterministically give us back one. Okay, but I don't want to spend a whole long time on that, so let's move on. Maybe we can talk about that more in class. It might be easier if I can point to things with my cursor, but I can't really draw on the screen. Okay, so that maybe gives you a bit of a feel for the language, but I think one of the things that's really important in how the language works is how the type system works. So what the authors have done is they have what is written as what's called a feature model that illustrates the types. I think it's probably easier to, this is maybe easier to look at once you're already familiar with the types. I'm not sure how much insight this gives you if you're trying to learn what the type system looks like. So I think it's probably easier if we actually just scroll through this and get down to what they have as, I think, a very nice categorization of the types. And then we can maybe come back up to some of these examples. All right, and they actually talk about this in terms of the values that you get. But the values, of course, are very closely related to the types you're working with. So I think probably a better introduction to the type system is to look at the values, but think about what the types of the values are. So what they've done is they've categorized the types of the values into these different buckets, and then really based on what the type of the data is in the value. So let's just start going through those. All right, so category A they have here is what's called predefined basic. And this shows some of the types then that OCL has as its basic types. Right, OCL has integers, real numbers, strings, and booleans. And this is one area where it's helpful to scroll back up a little bit, because what we see is that we have what's quite often called a type lattice. We don't need to get into that a whole lot, what that actually means, but what it essentially shows is how types are laid out in the system and how types are inherited from other types, or maybe a better way to think of this is when a type is substitutable for another type. And what we have here with the basic types is we have at the top something called OCL any, and if you think about languages like Java where most of your types involve classes, OCL any would be similar to the object class. Right, where we say that any class in Java inherits from object anytime that we have a parameter of type object we can really give it a class of, an object of any kind of class, right? Because every class can be used as class object. And so a common way to write containers back, I guess, in earlier versions of Java, before generics were introduced, was to say that you just had something like a list of object or a set of object. And then what this really meant was that you have, it's not that you really usually have object in there, it's just that this gives you a way to put anything in. The difference between that and this is that OCL Any doesn't just say, so here we have our classes, and we see that, as we would expect, if we have this inheritance relationship between C1 and C2, where C2 is a subclass of C1, this is actually modeled in here as well, where C1 is the more general class and it's higher up. Basically, the more general things are higher up in this diagram. And we see this doesn't just work on here. If we replace OCL Any with object, then this would look a lot like something like Java. If we take our example from the exam, this would be something like animal, or dog, animal, and then object up here. Instead of just working with classes, though, this actually works with the other types as well. That's one big difference. In Java, if you have an integer, a scalar value, not something like a big int, then this isn't related to object. Where, in this case, they do some things with some boxing and unboxing and stuff like that I don't really want to get into, since we're not discussing Java directly. But the actual type, if you just write down 5, this isn't an object. But here what we're saying is that OCL Any is really, this means it's anything, right? If you have a value that winds up with this type, it means it just really could be anything. And then you have OCL Void, and this is essentially nothing. And this just means you don't have any type information at all, and you don't know what it is. But if we look at integer and real, this works, I think, in the way we would expect, at least the way we would like, where we say that real is the more general type. Right? So real includes all the integers. Any integer, if you have 5, you can treat it as a real number. You can treat it as 5.0. But you can't do the reverse. You can't say that a real number, 5.0, is actually an integer. You can do things like truncate it, but then if you have 5.1 or 5.2, you don't have a way of directly going to an equivalent integer. So this is really, for these types, you could view this as, in some sense, inclusion. The integers are included in the reals, and then all these values from all these other types here are included in OCL Any. Okay, so let's go ahead and go back down here. And so again, we have these 4 types. We have string, boolean, real, and integer. And we have this relationship where all integers are also reals. Number 2, we have what are called enumerations. And this is similar to enumerations in languages like C and C++ and Java, where what we want to do is say that we have some information in the model, like the kind of branch in this case, and what we want to do is we want to have a way of some name for referring to that. And so we, in this case, there's 2 different ways to do it. One is to put these pound signs before them, and so we have branches for rental car places that are at airports or downtown or someplace on the road. Newer notation is like this, where we use what looks more like C++ namespace notation, where we have, and this is also just the package notation that's used in UML, which we talked about last time, where we have branch kind and then colon, and then airport. And so airport, just like up here, is one of the enumeration values that we could use. So if we said that something was of branch kind, then it would hold one of these values. C is classes, and so this is actually just the classes we define in the system, right? And so if we have classes named something like car or branch, then we have values, and these values in this case are just really arbitrary names. We would expect that these would actually be objects in our system, just like these are things like airport and downtown are actually values. They're just values of this enumeration type, and something like 42 or false or 43.44 values of the built-in types. So we'd have all these different values representing objects, and if we had something like an object diagram, we should have an example of these at the end of class last time, then these would be maybe the names of the items on the object diagrams. So that's what they call the atomic types, and then they have what they call the template types. And the first set of template types are, or I guess template really values, but again they're grouping these into types, are parameterized. And so what we see for these is that OCL has a bunch of different built-in container types and also structured data types. And so if we scroll back up, again, sorry for all the scrolling in here, we actually see them here. We have what are called sets, and these are just what we think of as sets, essentially unordered collections of information where any item can only appear in a set once. So if I have a set with 8 twice, it's the same as the set where 8 only is in there one time. We have bags, and these are also referred to as multi-sets. And we'll see some examples of those. I guess we can see an example just right below here, where we have something like this, where we have bag, and then we have 42 in there twice. And for a set, this wouldn't make sense because it's the same as having it in there one time. But with a bag, in essence, we don't remove duplicates. We keep them. We keep count of how many times things appear inside the set. So a bag can have 42 twice, and if we wanted to say compare with a bag that only had 42 once, they would be different because this, the number of times something occurs is also important. We have ordered sets, and ordered sets are somewhat of an odd entity to have in there because sets are by their very nature unordered. But this is essentially something that is like a set, but where the order of insertion is important. So something like 7, an ordered set with 7, 8 is different than an ordered set with 8, 7, because the order that things are put in is kept track of. Right, and then we have sequences. And we'll look at sequences in a bit. But these things all wind up being collections. So collection is much as we had over here, where we say we have this hierarchy. This hierarchy, an important point to note is that it only applies to the non-collection types. Right? We have integer, real, string, boolean. We have our classes. We have enums. But we don't have sets and bags and sequences and ordered sets over here. We have them over here instead, and we have this general way of referring to these, which is as collections, and then specifically we can say what kind of collection it is, whether it's a set, a bag, a sequence, or an ordered set. Okay, so let me scroll back down. And so these are the examples we see here, where we have, again, these are parameterized. You could view these the same as being with generics and in a language like Java, where we have a set, and we have a set which is just of t, so we don't know what it is yet. And then when we actually put types in there, we start actually getting information about them. And so that is described somewhat here. Right? Parameterized types also possess at least one type parameter, and they can also be nested then. Right? So we're not just restricted to having a set, but we could also have a sequence of collections or sequence of ordered sets. Along with this, we have tuples, and what they call tuples are much more similar to what are normally called records, where we have fields, like part 1 and part 2, and those fields have types. In the case of OCL, the reason I'm saying they're more like records is because they are unordered. You also have this named value mapping. We'll see when we see examples of these, and the order is unimportant, and that's like records, but generally with tuples, the order is important. So it's maybe, in my opinion, not the best choice of a name. Okay, so that gave us those, and then, so parameterized is sort of a general category they have in here. And then we actually have this breakdown of these different collection types. Right, and also tuples. So parameterized included tuples and things like sets and collections. And so what we'll do is we'll look at several different types of these. What they categorize as concrete flat, concrete nested, and abstract nested. And then they say they have one here which is unpopulated, and we'll see what that means. All right, so this first one, which is what they called the, let's scroll back up, my short-term memory is failing me, what they call concrete flat. Really what they're saying is that we have something like a set, and the things it has in it are atomic values, right? It doesn't have this nesting of, say, other sets, ordered sets, or whatever inside. So here we have sets of integers. Here we have a bag of integers. And again, the fact that 42 appears in here twice is significant. Sequences, ordered sets, sequences again, and so on and so forth. And the types with these are as you would expect. If I put integers in my set, then I get a set of integers. If I put integers in my sequence, then I get sequences of integers. Sequences are basically just acting as lists here. See, if I put these into a sequence, I get a sequence of strings. And so I think these are really, up until I get to maybe to this line, are all pretty much what we would expect. I put the same thing in, and then the type here is the type of all the elements, and all the elements have the same type. When I get to here, I have a set of 42 and also 43.44. What I need to do to figure out the type is I need to look at that diagram and see if I have multiple things, which thing is the highest up on the diagram. So that was here. I had an integer and a real, and so it must be the case that because the real is higher, then that is the type that I'll put in there as the element type. So I guess I don't have to scroll back up in a sec. Keep this picture firmly in mind here. And then as we look at the next line, I guess the last line, the next line works on a similar principle. I said I have a blacklisted subclass of customer, and so if I put a blacklisted customer and a customer into a sequence, then what I get is a sequence of customers, right? Because I can treat blacklisted customers as customers, but I can't treat normal customers as blacklisted customers, so I have to put the superclass in there. I have to go, again, up as high as I can in that diagram. And then the last line, which is really where you need to have that diagram in mind, we get OCL any as the type. And you may wonder why. Well, that's because this thing that we have here is some kind of a class type. It's an object, which is probably, I'm assuming from the name, of class car. And then this is a string. And if you put one finger on the class type on that diagram and one finger on string and you went up, the first time they meet is when you get to OCL any. So that's the type of the set. It's basically a set that can have anything in it. Okay, so that's this category that they give here of concrete flat. Concrete nested, pardon me, then just says, I then have nested containers. I have sequences of bags, I have sets of sequences, and the sequences have sets. Right, so I can do this arbitrary nesting, but at the end of the day, the data types are really the same types as they are here. When I get down to the bottom, they all result in something like a number, or, really here all the examples wind up as numbers. But they could also be classes, enumerated types, strings, real numbers instead of integers. The key thing here is this nesting. And then there's this last category, what was described up here as abstract nested. And what this is saying is that instead of just the things we had up here, then I can also have things like tuples inside. Right, so here I have a set, and the thing that the set is made up of isn't these, it's basically other structured types. And not just sets of sets that wind up having numbers in them, but sets of tuples. And in this case, instead I have a set of a set of 7 and a set of bag. And it's really this, the fact that I have this difference here. So I wound up, instead of having, here I had a bag and a bag, and so I get a bag. Here I have a set and a bag, so I get a generic collection. And so that's really what pushes that down into this category. Right, so I have a more general type. Of course, the things I'm looking at, I actually know the types because I have the values written down. But the type that if we say I had this in the variable somehow and we were just looking at the variable, it would be a set of collections of integers. Okay, so there's 2 additional categories that do have things in them, and these are these tuples, and the distinction, I won't dwell on this much, but the distinction between these 2 is H just has tuples, and I has essentially tuples that contain other tuples. And so this gives what do they call in the paper, flat tuples and nested tuples. And then they also talk about, again, this isn't something that I think is, please just read the paper, I won't dwell on much, but this is what they call abstract flat structured collection. What they say is that they have this category and there's things of these types, but you can't actually build them. And so that could be something useful to know. So, okay, so this was actual values, and then looking at the types of these values, and I think this maybe gives a better introduction to the type system than here, so maybe look at that, maybe keep that in mind as you're looking through here. I think this is still quite a nice intro, but it helps to actually see, I think, lots of examples here instead of just looking at class diagrams and such. But once we have gone through that, once you go through this part of the listen to the lecture, please, I guess, start up here again and look through and read the description of the type system, and it's good, if nothing else, to get the terminology down. Then we have things like atomic types versus class types versus enumeration types. Then we have flat types versus nested types, and we showed examples of all of these. And then we looked at this, so I think this should be familiar to you now. An example of putting this into practice is really here, showing how the various things are related. And I'm not going to go through this in detail. I can go through this in class if people have questions about it. But really, this is just showing how if you start putting various combinations of things together, how they will be treated. Right. So essentially, what they talk about here as induced types. If you start combining things in certain ways, then you can change the types. Again, we saw that if we put a number together, an integer with a real, then that's a real. If we put an integer together with a string, we get something that's just OCL any. And so as you put different things into collections, you can change the collection types. So, again, I won't dwell on that any further, but maybe we can look at that in class. Okay, well, for now, let's go ahead and move on. What they cover next, and I think this is useful because this you will probably run across as you're using OCL. You see things like sets and ordered sets, and you may wonder what these mean in terms of when are things equal, or when are things not equal. And this actually describes this in some detail, so you can see, for instance, here they say, well, if I have a set that has 7 and 8 in it, that's the same as a set that has 8 and 7 in it. And it's also the same as a set that has 7, 8, and 7 in it, because the fact that 7 appears twice doesn't matter. In general, each of these things have 7 and 8, and so they're all the same. With ordered sets, the order becomes important. So the ordered set of 7 and 8 is different than the ordered set of 8 and 7. And so I think that's easy to understand. This part here is maybe a bit more confusing. Really what this is saying is, because it's a set, it doesn't matter if 7 is in there multiple times. It just matters if it was put in there first. And so the set with 7 and 8 is the same as 7, 8, and 7, because it has the same elements and they were put in the same order. And this is why these two aren't equal, because here 7 was put in and then 8, here 8 was put in and then 7. We also have similar diagrams for bags and for sequences, where here the order doesn't matter. So a bag with 7 and 8 is the same as a bag with 8 and 7, but neither is the same as a bag with 7, 8, and 7, because here 7 appears twice. And then sequences, the order is important. These are essentially lists, and then also the number of times things are in there is important, because we have what's essentially a list. So if it appears in there multiple times, it's just in there multiple times. So the only time the sequences would be equal is if it has the same elements in the same order. So these two are not equal because the order is different, and then neither of these is equal to this bottom because this has 3 elements, while these each have 2, and then the order is also different. And they categorize these then as whether something is insertion order insensible or sensible, meaning it doesn't matter the order you put things in, and also insertion frequency insensible or sensible, so does it matter how often things are put in. And then there are a couple of OCL expressions that work with these types of collections. Probably the 2 most useful ones are including and includes. And these are the ones I know. There may be others. But with collections, these are sort of the basic ones you'd want to use, because this including actually puts something into the collection, possibly building a new collection. So if the collection changed, if I include something into a set that's already there, then I have the same set I started with. But if I include something into a sequence that wasn't already there, I really have a new sequence. So including adds things into the collection, and then includes actually, which is here, actually asks if something is in the collection. And this is actually, these 2 are how they define these properties up above. Okay, so let's go ahead and continue on. I will post, we will be using a tool called Papyrus, and I will post some information about that, and I'll see if we can do something similar there. It's using one of the OCL tools they mentioned in this paper, but it's not using the one they're actually using in the paper. So I'll see if I can find the one they're using too, because it would be nice to actually play with some of these properties. Okay, briefly, OCL also has null. And so that is, if we type null, we get OCL void. And OCL has null for the same reason that other languages have null. Sometimes it's useful to use it. Right? Sometimes something is just undefined. Sometimes we want to specify that something is undefined. Sometimes we just don't have complete information, and so we may just put null in those cases. And then we also have this OCL is undefined, which serves a similar purpose, and that's mentioned up here. Pardon me. Okay, so next let's look at navigation. And we've already seen navigation some. We saw this with some of the properties we were writing. What I would encourage you to do is to look through this section, and again, I'll see if I can maybe get this example in this tool so you can actually run these examples yourself. But what this does is this has a variety of examples of navigating through a model. So this is really what we want to use OCL for, constraints, and also to give us this kind of navigation and querying capability. So how do we do that? Most of it we actually get what we'd expect. So if we say car, we get a car. If we ask for the registration number, then we get a string because that's what that was defined as. If we ask for the car group, then we get a car group, and so on and so forth. Right? There's a couple of things to keep in mind. One is that if we actually ask for a car group like this, what we say is that what we get is, because we get this set and it has these 2 things in it, right? So a car is a member of a given car group, but a branch has multiple car groups. And because of this multiplicity, what we get back is we get back a set. And I think this is probably what we would expect This one is a bit unusual, so if we ask for cars, we get back a bag, and sometimes we even get back a bag when we have the same thing in there twice. And of course, if it were a set, we would only really have it in there once, because it would, the two occurrences, one of them would just go away. But you may wonder, well, why is this coming back as a bag instead of maybe as a set, with just the date in there one time? And this is because if there's multiple paths that you end up navigating, or if you go on the edge twice, so if we actually were to go look at the rental one and then the driver, so I guess let's scroll again. All right, so we have a rental. I guess it shows it here. And then we have a driver. So the rental's over here and the driver's over here. And we have one or more drivers in a given rental. If we, I'm sorry for all this scrolling, let me get back down quickly. So here's the actual diagram that is being queried over, I believe. So we have one rental, but we really have two drivers. And what we notice is both drivers have the same birth date. It's date 1 here, it's date 1 here. And so when we ask for the driver, we get the two drivers back. But when we ask for the birth dates, because we had two separate drivers, we get back two separate dates. And it just so happens that the date is the same. It didn't have to be for this example. But in general, when we navigate through a set, so we had a set here of drivers, when we navigate through a set to another piece of information, the container will get back as a bag, because it really keeps track of the fact that it went through these, these different elements in the set. Okay, and then here we have a null, and yeah, so I'll just leave it at that. All right, so continue, looking through. Again, I'm not going to keep encouraging you. Please read the whole thing. What we see here is OCL has the same types of logic operations that we looked at with propositional logic and predicate logic, and so we can start putting things together into more complex expressions. We have, in this case, what they call a three-valued logic, and what that means is that we have things that are true and things that are false, and then we have some other value, and then that value, we could say that is some kind of, like, we don't know type of value, and here that's null. And so our truth tables look a bit different because we have to account for null in them. So I guess I would encourage you to look at the truth tables carefully because of that addition, but if you drop out the part that's null, then these truth tables look basically the same as the truth tables we've already looked at. If we have an or, and we have false, and we have true, then that gives us true. Same with and, that has the traditional rules. Exclusive or, what this is this is or, where, but we really are saying that one is true or the other is true. But if we have the case where both are true, then that gives us false. With implication, equality, inequality, and then if we have, like, maybe this is something which is a little different if you're familiar with databases. Quite often in databases you can't compare null values. Here null is just treated like a normal value, so you can actually say, is null equal to null, and this will be true. Generally, if you try this in a database, it still says it's false, and you have to do some kind of special check to see if something is null. Along with these various logical connectives, we also, just like in predicate logic, we have universal quantification, we have for all, and we have existential quantification exists. One thing that's important to know is that these range only over finite collections. So we can't do something like, say, for all integers or for all strings. What we do instead is we say something like, for all members of this set, for all members of this sequence, where there exists a member in this bag. And we also, I don't know how important it is, but we have ranges. And so I talk about ranges. These could be useful in some cases. And we do see ranges in the diagram. So we have things like 1 dot dot 3. Okay, so collection operations, we have including and includes, which I already mentioned. We also have excluding, and excluding just removes all occurrences in the element from the collection. The all occurrences is important to remember, because as you'll see, if you go down to something where this matters, so if we have an ordered set and we exclude 6 from it, then what we get back is we get back 9, 7, 8, and I would have assumed that 7 would have also been in here, so I'm a bit confused as to why they're saying that this is true. Maybe this is actually a bug in their example. But if you say excluding 6, then it doesn't just remove the first 6, it removes all of the 6s that are in there. Right, and I don't think they have any, well, they have other examples, but we don't really see them acting as removing all. I guess we see it here as well. So if we see, if we exclude 8 from the set of 7 and 8, we just get a set of 7. If we have a bag and we exclude 7, and we have 7 in there twice, then we just get back a bag with only 8. Now notice we don't get back a set with only 8, even though this would also make for an appropriate set. Bag is part of the type, so the type doesn't change. We have includes all and excludes all, and these are actually checks. So here we have the sequence, and we say that, does this include everything within the sequence? And so you see, this just tests membership. And so we have also excludes all, and this would essentially remove these elements from the ordered set. Okay, is empty not empty in size? And these give us, I guess, these are the typical types of checks that we could do. These, I think, should make sense just looking at them. If we have a set with 7 and we remove 7, then we ask if it's empty, it's true. If we have a bag of 7, we remove 8, which wasn't in there, and we ask if it's not empty, it's true. If we have a set and we ask what the size is, it's 3 for this case, because the 2 7s and the 2 8s only count for 1 each. But if we have a bag with the same, it's 5, because we keep track of how often they appear. The size of sequence is just the number of elements in it, and then the size of an ordered set, again, keeps track of the order, but it doesn't keep track of duplicates. So these 2 7s, we just count for 1, and we have a size of 3. We have select and reject operations, and we can use these to do filtering. So select we saw earlier, reject is really, I guess you'd say, sort of an anti-filter. Instead of matching everything that, or I guess pulling out everything that meets this condition, what it says is to get everything that doesn't meet the condition. So here we're basically saying reject everything. What we do is we find everything that's odd and we reject those, so the only things we keep are things that are even. That's why we have a bag of 8. We also have collect, and collect just gives us the ability to, in this case, just apply an operation over everything in the collection. So here we just multiply everything by itself. And this can change types, like we see here. The set gets turned into a bag. So this ordered set gets turned into a sequence. And here we do something which is, we just categorize everything as even or odd, so the set gets turned into a bag. Okay. We also have some other collection operations, and these are 1, any, is unique, and sorted by, and 1 is, I guess you say, similar to something like the 1 set qualifier in alloy, where we're saying that this is true when we have exactly 1 element that meets the predicate we give. And so this is the case here, where we say, this is the case if I have 1 thing that's even, And this is the case if I have one thing that's odd. But this is true because we only have one thing that's even. Here we have two different elements that are odd, so this is false. What any does is it says, just check the formula and then give me back anything for which the formula is true. And the problem we get into here is that at this point we also see we have, my apologies, my battery is almost out, so I need to go plug in. Because we can pick any of the elements, the element that we select is completely up to the implementer to choose. So it could be 7, 8, or 9. Okay, so as I was saying, for this, what we see is that this is, to some extent, an implementation decision, and this was part of what was meant earlier by OCL being a specification language. It doesn't really dictate how the implementation should occur. So if you say, essentially here, just give me back anything from the set, it could be 7, but it also could be 8, or it could be 9. Right, we could get back something like void if we have a condition that doesn't return anything and we're assigning that. So I guess one thing I didn't mention is that we also have this let construct, and this is something which would be similar to let in functional languages, where we're actually assigning C to the result of doing this. Right, so here what we say is, we basically carry out this computation here, and then if we are binding it, we would get back a value. If not, we're just getting back nothing. Okay, so we have is unique, sorted by, some of these other checks. I won't dwell on these. We have set union, right, which works as we would expect from, I guess, from normal sort of set operations. We just get back to things that were in both. If we do union over bags, then we just put the elements together, and while here we add 8 in there twice, and we just get it once because it's a set. And here we maintain the duplicates. And sequences, we really just paste them together because these are lists, so we just put one and then the other. Along with all these, we have various ways of converting between the different kinds of collections. And so, a sequence we can turn into a set or into a bag. And the difference here, again, is just the difference between sets and bags. Some of these are also implementation dependent. So if we turn a set into a sequence, of course the order of elements in the set that wind up in the sequence is really up to whoever writes this at the end of the day. Whoever goes through and figures out, because we have 8, 7, 7, 8, whoever figures out whether 7 or 8 comes first. And both of these are allowed. Here again we see some implementation, I guess, sort of leaking out into the way that the system works, because again we're turning the sets into a sequence. And we can also do things like flatten, and that's just if we have sets which are inside here, then we just, what we want to do is we want to take the elements out and just put them directly into the sequence. Let me get rid of that. I'm assuming you guys are seeing my OS X update message. So, okay. Okay, this is something I will leave for the paper. This is something we may wind up using if we really use a lot of OCL. So we've looked at various things that look like iterations, where we say, I want to see if something is true for all elements in the collection, or I want to get any element of the collection that meets some type of condition. And you can imagine just going through the collection and checking the condition until you find the element that matches that. Well, there's a very generic iteration construct called iterate, and they describe that here. And they give an example. But as I said, I'll go ahead and leave that to the paper because I think it explains it fairly well here. Okay, tool support. Now the tool that we'll be using is one called Papyrus. and they do mention that here. Well, they mention it somewhere. There it is. And Papyrus actually uses this MDT OCL component, which they talk about back here. Right, so there's really two general OCL parsers that we mention. One which comes with the model development tools in the Eclipse project, and this Dresden OCL. There's been a bunch of, so these are, I guess you'd say, sort of dedicated OCL tools. And then UML tools with OCL support, and there's actually quite a few they list here. Rational Rows, Argo UML, Enterprise Architect, Magic Draw, Borland Together, and then Papyrus. And we'll be, like I said, taking a look at that because it integrates nicely with Eclipse, and it has some good support in there for working with models, for drawing UML diagrams, and for using OCL. And coming near the end, they talk about some verification and validation tools for OCL. Part of the thing that may come out of, I guess, looking at all these is that checking the syntactic correctness is, of course, necessary. You want to make sure that the expressions that you're writing are actually valid OCL expressions from a syntactic perspective, but you'd also like ways to make sure that they make sense. Right? Are you writing an OCL expression that, where you're navigating through a UML diagram and you're doing it in such a way that you would actually get results? Or are you adding some kind of constraint that makes sense? And we're writing these are, in some sense, like little programs, and so it's possible for us to make mistakes. And so they discuss this a bit here. There has been some work on this, including some work in turning UML into Alloy. There's also been a fair amount of work on the semantics of OCL, but as I mentioned somewhere in this paper, there isn't currently a definition, a full formal definition of OCL, and so this isn't something you could imagine. If you had this formally defined, you could maybe have tools that would check it, but the fact that you don't have a formal definition of this means that there's tools that do a lot of checks, but in general, this isn't something where you can just always verify this. And I believe they even mention it here that this is essentially undecidable. We talked about this with predicate logic. You could imagine, there's some OCL you could write, and you could try to apply it to lots of different models, and you don't actually know if any model that, that I guess had the stuff that you needed that you mentioned in the OCL formula. It could be that you could just keep coming up with an infinite sequence of models. So actually being able to check to make sure that this is something where the OCL you wrote is always valid or always gives you the result you're looking for is something that we really can't do. But there's a lot of tool support that I guess helps, and that in some cases can show us that we've actually done this correctly. And finally, code generation. This is one of the things that we would like to do. There's been some examples in here of things that look an awful lot like code, and so we could imagine that we'd like to take these OCL expressions and turn them into code. They mention a couple of options here of what's typically done. Things like, for instance, you could turn these into triggers in the database, and then if you try to do the wrong thing, the trigger would fire, and it would invalidate the insertion or the update. You could think about using these in various transformation tools. So there was a mention of ATL here, I believe, and I'm just missing it now. There's a transformation tool called ATL, which stands for A Transformation Language, and that uses OCL as well. And so, the thought here being that you could do something like transform the model into code, and you could use OCL to identify pieces of the model that you're matching. It may also be possible to use OCL that's in there to provide functionality to then generate code with that, although I'm actually not sure if ATL allows that or if it just uses it for matching. Okay, and then I think I'll just go ahead and let you guys read the rest of the paper. This talks some about reasoning techniques and possible extensions to OCL or work that needs to be done in the research community, and maybe some limitations of the way that works. So, one of the problems being that the OMG is really not an open group, and so a lot of people who are doing research on this, it's very challenging to get your ideas into the OMG. Well, at that point, we're done going through this. Hopefully, then you have a better idea of what OCL is, how OCL works. We've looked at quite a few examples of OCL along the way and talked really at length about the type system. I think that's really an important thing to get your head around, because so much of the way the language works is based on the types of things in the language, both in terms of the data that you're manipulating and the types of operations you have available. So, definitely please go back and revisit that. Take a look really in detail at that. Again, I'll try to post some type of information and hopefully some sample models, and we can kind of experiment with this. It's going to be part of the homework anyway, but hopefully I can post something where you guys can just sort of start taking a look at this and play around with something like an OCL console, type in some of these expressions like what we see here in the paper, and get comfortable with the syntax and how it works. Okay, well, thank you, and I will see everyone either online or in class on Thursday.